Look at all these dogs. Some of them are different sometimes.
How does that happen?
Different genes make different genotypes, which mean different phenotypes.
What does all of that mean?
A genotype is made up of two alleles, generally designated with letters. And different genotypes result in different phenotypes. A phenotype is the characteristic caused by the genotype, such as a flower being red, white, or pink. What kind of different alleles are there? Well, there's dominant, recessive, or codominant. Dominant alleles are generally represented with an uppercase letter and recessive lowercase. A dominant allele is called so because if you had a capital letter and a lowercase letter as your genotype, your phenotype corresponds to the capital letter. So if it's a dominant gene, the only way you can get the phenotype corresponding to the recessive gene is if you have two recessive alleles. Codominance is interesting to note because, say the lowercase letter, the recessive phenotype is a white flower, the dominant phenotype is a red flower. Well, if this was a codominant gene, then the uppercase letter, lowercase letter would be a pink flower.
A homozygous genotype is one that has two of the same type of alleles, and a heterozygous genotype has two different alleles. In this presentation, we will be looking at a variety of topics, including autosomal inheritance, X-linked inheritance, inbreeding, and how Markov chains can be linked to genetics. Autosomal inheritance is when an offspring inherits one gene from each of their parents, whereas X-linked inheritance occurs when a gene is on the X chromosome of an organism, and in that case, males only inherit one X chromosome, where females inherit two. And inbreeding is when members of the population breed with close relatives, and this can cause genotypes to drift towards extremes.
And now for genetics.
Checkmate!
Autosomal inheritance. You inherit one gene from each of your parents. What the is this? Did you plant this, Mr. Bruno? Is this what the cameras are for? I came all the way over here to enjoy a game of Iriopoly, and you turn it into some bull for your linear algebra project? I canceled game day for this. What heck with you losers? I'm out of here.
What's autosomal inheritance?
I'm glad you asked. Alright. So, under autosomal inheritance, each individual, and you're gonna wanna pay attention to this. Each individual, no matter their gender, has two genes with possible genotypes. Cap A lower a, or of course lower a.
When individuals mate, their offspring inherit one gene from each of their parents.
That sounds like a lot of... Can you give me an example?
That's the stupidest question I've ever heard. Can I give you an example? Of course we're going to give you an example. Have you never taken a math class before? They always give you an example.
Pompous math majors.
Alright, let's keep going.
Okay, x0 is going to be our vector of initial conditions, where a sub 0 is going to be the initial distribution of the genotype capital A, and here we're going to let all of these equal 1/3.
An evenly distributed population.
B sub 0 is the initial distribution of capital A, lowercase a, and C sub 0 is the initial distribution of lowercase a.
And because they're fractions of the overall population, it's going to have to add up to 1. Okay, it stands to reason that this is true of just about every generation. Now we were talking about initial, now we're talking about any generation past the initial. It's just going to be represented by x to the n with these components, a n, b n, c n, and they're representing the same thing, the nth generation's distribution of this genotype, and this genotype in the nth generation. And it's still a fraction of the population, so it's still going to add up to 1.
We can find the probability that an offspring has a particular genotype by completing a Punnett square.
And in case it's not clear, you just meet in the middle.
Yeah. And we can see from this one that when you breed a chicken with capital A genotype and capital A lowercase genotype, their offspring will have genotype capital A with probability 1/2, and genotype capital A lowercase a with genotype with with probability 1/2.
Okay. And now let's construct a probability table from Punnett squares. Alright, so we did all the Punnett squares, so you don't have to, but if you want to double check, it's your prerogative. And as you can see, genotype of the parents, do the Punnett square for those, and then you can understand the probability. There's certain here, half-half, certain, a little less certain. And this is going to be our probability table, which we're going to be able to narrow down for our probability matrix.
And since we're always breeding a hen, no matter her genotype, with a rooster of genotype capital A, our columns of our probability matrix will come from these columns in the probability table.
Alright.
And so we can construct the probability matrix M from the columns we showed on the probability table. And we can use M to find the nth generation by multiplying M times the previous generation's distribution. And so if we multiply M squared by the distribution of the genotypes 2 generations back, we will also get the nth generation. And so this pattern continues down until you get to m to the n times our initial distribution equaling x to the n. Hence you can see it's going to be very useful to diagonalize m so that it's easy to take powers of it, because taking n powers of this would be quite difficult.
And just so we're clear, just the way we get from here to here, remember x, the generation is always the probability matrix times the last generation. So that's where we got that from.
Okay, we diagonalize m by finding the characteristic polynomial from the determinant of lambda I minus m. This yields lambda times the quantity lambda minus 1 times the quantity lambda minus 1/2. Setting that equal to 0, we get lambda equals 0, lambda equals 1, and lambda equals 1/2 as our eigenvector values. This yields the eigenvectors 1, -2, 1, 1, 0, 1.
It's 1, 0, 0.
Yep.
And
one,
negative
zero,
1,
zero.
1, 0. And we encourage you to go through this yourself, double check, make sure you remember diagonalization, but we skipped it because this is something that we should already know how to do. Say okay. So rather than raise m to the nth power, we're going to diagonalize it and raise this to the nth power. And how do we get this, Jake?
P and D, well, P is constructed from the eigenvectors that we found, and D is constructed by the diagonal elements being the eigenvalues that we found.
And of course P inverse is just the inverse of P, and if you actually multiply this out, you should get m, right?
Yes, and recall that the reason it's easier to take powers of a diagonal matrix is because the P matrix and the P inverse matrix cancel out with each other when you raise this whole expression to a power. So it ends up just being P d to whatever power you're taking it, P inverse.
Dot, dot, dot. So you're left with the n piece, you're left with the other n piece, and d to the n in the middle. Beautiful.
Okay. Going back to our equation for xn, we can substitute in the P dP inverse for the matrix M, and here is x0. If you multiply all those out, you get this matrix, which we can turn into a system of equations to find a sub n, b sub n, and c sub n. Alright, from the matrices we multiplied out, we get these equations, and the equation for a sub n simplifies the expression a sub 0 plus b sub 0 plus c sub 0 to 1, since these are the initial distributions of each genotype in the population. And then we can take the limit as n approaches infinity for each of these equations, getting a sub n approaches 1, b sub n approaches 0, and c sub n equals 0.
So, our breeding program was very successful. All our chickens are going to be large-breasted, and we're going to make a lot of money off of some murder.
Yes.
Cool.
Pompous math majors.
Welcome. I hope you've enjoyed the presentation so far. Now we're going to get into something new. We're going to use linear algebra. We're going to use matrices. And we're going to predict genetics. We're going to construct a probability matrix to estimate what the royal family's hemophilia chart is going to look like. And we're going to do a side-by-side comparison when we're done. So we're going to construct a probability matrix, which we're going to call M, and then we're going to multiply by the previous generation to get the new generation. Sub R, because these are the people in the generation that reproduce. This is an estimation, but it's going to come out pretty accurate, as you'll see at the end of the demonstration. I hope you enjoy it. Say okay. Let's set up the probability matrix. We're going to get the probabilities from Punnett squares, which if you've had biology in high school, you probably remember, but just in case, let's go through it. So first, let's do a healthy female, healthy male. Classic example, we know we should have a 50% chance that it's either a healthy male or a healthy female. So it doesn't matter which side you pick, just line them up, 2 by 2, line them up, x, 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 x. So 2 females, 2 males, 4 choices, 1/2, 1/2. So this corresponds to 1/2, 1/2, 0, 0, 0, 0. And the reason it turns into this is because the vector we're going to use is going to go healthy male, healthy female, carrier female, affected male, and then an affected female, which is very rare, we're not going to get any of these, and then we're going to have to add a 0. Now the reason we have to have a 0 is because we have to have 1, 2, 3, 4, 5, 6 of these things. The reason we have to have 6 of these things is because there's 6 total combinations. Work with me here. We could have healthy male, healthy female. That's 1. Healthy female, affected male, carrier female, carrier female, healthy male, carrier female, affected male, affected female, again very rare, healthy male, affected female, affected male. So that's why, and clearly there's only 5 possible genotypes. If the 6th did exist, it would be, this does not exist. It's an X-linked recessive, so no good, never going to happen, impossible, doesn't make any sense even, so we're just going to call it 0. Alright, so now we go to our probability matrix. We got our first row, healthy female, healthy male. Now we're going to do what we're actually going to cross, a healthy male. We can just separate it so it looks pretty. Healthy male, carrier female. How are we going to get the probability matrix, the column vector for this? Same process. Punnett square. So here's our healthy male, that's Albert. Here's our carrier female, Victoria. Line them up. We got a carrier female here, healthy female here, healthy male here, and an affected male here. So 4 different choices. So everything has a 1/4 probability. So now And on the what, we're going to have, remember, we already discussed it. It goes healthy male, healthy female, carrier female, affected male, and then a 0. There we go. So this one is just 1/4 all the way down until we get to the affected female, 0, and then we get to the 0 row, which is going to be 0 all the way across. Okay, and now let's fill in the rest of the probability matrix. Okay, so I got the probability matrix. If you want to double check, you're welcome to do the Punnett squares, but I got it right here. Nice and big, nice and pretty. Remember, we have our 0 row. These are offsprings, these are the combination of parents. Alright, hopefully you can see that okay. Try not to stand in the way. Alright, let's get this on the road. So we got healthy parents, carrier female, afflicted female, affected male, healthy female, 1, 2, 3, 4, and then the very rare case, but still possible, affected male, affected female. So I'm going to fill this in for us, and then we're off. We already talked about that, row of zeros, it's not possible. Just in case you forgot, in case you paused it, get a coffee, some ice cream, or whatever. Alright, and now, alright, continuity errors. We are not film majors, which surprisingly is a major at Edinburgh for whatever reason.
Yep, and right now with one places you only have another.
I'm recording, Jim.
Oh.
Voila. Probability matrix. Alright. Now, here's how we're going to find out what each successive generation is going to look like. We're going to get the nth generation, which again is going to be a column vector, and it's going to be a fraction. It's going to be a fraction of how many people are healthy males, healthy females, same column vector we've been using, it's consistent, and it's going to be equal to the probability matrix, which we're going to call this M, times, and this should make sense, the last generation, because the only way you're going to get a new generation is if the last generation breeds. Alright, so now, let's talk about the different kind of vectors we're going to get into here. Say, okay, now let's talk about the notation. Notation's important here, it's not very confusing, I made it very self-explanatory. Vector x, that's just the fraction of the population, and now parentheses n, in this case 1, that means we're talking first gen. And now there's 3 different kinds of vectors for each generation. There are the probability vector, and we get that by just taking the probability matrix and multiplying it by the last generation who reproduced. So now, let's talk about subscript n. Again, first gen, this is just the actual number of children in this generation. How do we get that? Well, we take the probability vector and we multiply it by the actual number of children, which we get from historical data. We know Queen Elizabeth had 9 kids, and remember we got we got 1/4 all the way down and then 2 zeros. And when we multiply that by 9, we're going to get 2 1/4, 2 1/4, 2 1/4, 2 1/4, 0, 0. And we can't have a quarter of a kid, so we're going to get into some rounding here. So, just to make it as accurate as possible, we're going to strategically round. And again, historical data, we know Queen Elizabeth had 3 healthy females, so we're going to put the extra child there and round the rest down to 2. And so this is the first generation sub n, the actual number of kids. 2 healthy males, 3 healthy females, 2 carriers. This is projected, obviously. There is slight variation, but it's pretty accurate. As we're going to do a side-by-side comparison when we're done. But for now, 2 healthy males, 3 healthy females, 2 carriers, 2 afflicted males. And now the last notation we're going to have to get into is, again, first generation vector x subscript r, which we saw here. These are the actual, if you heard me before, these are the actual people in this generation that reproduce. Where do we get that? Historical data. So of these 9 children, 5 of them reproduced. Where do we place these 5 kids? Well, it's a projection, so we don't want to just model it. We don't want to just look at the data and say, oh, 1 here, 2 here, 2 here, none here. We're going to make a projection, and so we're going to do it random. We used an integer set random number generator, and the way I did that was there's 9 of them, so I just write out 1 through 9. And so if we just let the integer random number generator pick any integer here, it was 9 choose 5. So if it picks 2, it's right there. If it picks 4, it's in there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And in this case, the random number generator got us 1, 2, 1, 1, 0, 0. Alright. And that's the different notation we're going to be using. So now if I want Gen 2 probability matrix, remember I'm going to take m and I'm going to multiply by the last generation that reproduced, which is this vector here. So let's get into it. Say, alright, let's go ahead and jump right in. So remember, probability matrix is going to be, the probability vector is going to be the probability matrix times the last generation that reproduced. And remember, we just wrote it out, but I'll reiterate. The last generation that reproduced, Gen 1R, was 1, 2, 1, 1, 0, 0. And remember, these have to be fractions, so go ahead and multiply by 1/5, divide by 5, however you want to think of it. It's a probability vector. Even though it's the actual people who reproduce, it's still in terms of probability, so it has to add up to 1, the column does. So take m, multiply by the last generation that reproduced, and this is going to give us 3/10, 2, 3, 2, and of course double 0. And this is the probability of what the next generation is going to look like. So now I'm going to take this, and what am I going to do to get the second generation actual number of children in the generation? This is the probability that the children will turn out like this. How am I going to get the actual number of children that look like it? Well, let's see. We look at the historical data. She had 16 grandchildren. So I'm going to take this, I'm going to multiply by 16. Easy as that. And of course there's going to be some rounding here, but we're going to round strategically. And we're going to do a side-by-side comparison at the end, so you're going to see where these numbers come from. There we go. Easy as that. And now, there's one last vector in Gen 2 that I need. I got the probability vector, I got the actual number of children vector. Now I just need Gen 2, those who actually reproduce from generation 2. In other words, her grandchildren. And again, historical data tells us that 6 of these 16 children reproduced. So again, I used a random number generator because it's supposed to be a projection using probability. Probability is usually assuming randomness, and in this case we did. And using the same technique as last time, integer set style, just listing them out, 1 through 5, 6 through 8, etc. I got 2, 1, 2, 1, 0, 0. Alright. And now we're going to go through the same process and get Gen 3. Alright, it's time for the last generation. We're almost done, and then we can finally make that diagram we've been talking about and compare how accurate is this estimation. And it is an estimation. We're going to go through it real quick just to show why. But right now, let's get Gen 3. Alright. How are we going to do it? It's very iterative. We've done it twice already. We're going to take the last gen that reproduced, multiply by our estimating probability matrix, and just in case we forgot, this vector here is 2, 1, 2, 1, 0, 0 divided by 6. And what is this going to give us? This gives us a probability vector of, getting a little uglier here as time goes on, but 7 over 24, 5 over 24, and then it repeats. And then, of course, 2 zeros. Alright, so now let's take this. Historical data, she had 23 grandchildren. So we're going to take that, multiply by 23, do some strategic rounding, and we get which adds up to 23. Awesome. And we're going to stop at Gen 3, so we don't need to find sub R. And alright, let's get into the diagram of it. Cool. We got all the generations figured out. We finally did it. We got it plotted. Let's look at this diagram we've been talking about the whole time. On the other side of your screen, you're going to see the historical data, and we're going to compare, we're going to contrast, we're going to see. Remember, this whole process was an estimation, so we're going to see how accurate it turned out. So let's look at the top here. We got the queen, and we got her male, Albert. This is generation 0, remember. What did we find out? We found out Gen 1, they had 9 kids, probability matrix of 1/4. 1, 2, 3, 4, 5, 6, 7, 8, 9 kids. Remember, we had 2 healthy males, 3 healthy females, 2 carriers, and 2 afflicted males. Alright, and now remember, of these 9 kids, 5 of them reproduced. So everything we talked about, it's plotted, it's real pretty. This side is the healthy people, these are all the afflicted. And now let's do some comparing and contrasting. So Gen 1. In reality, on the other side of your screen, you're going to see Gen 1 had 2 carriers and 1 afflicted male. We had 2 carriers, 2 afflicted males, so pretty accurate. And then 3 males and 3 females. We had 3 healthy females, 2 healthy males. Obviously, the 3rd healthy male in our case turned into an afflicted. So we're only a little bit off. That's pretty good. Now let's look at Gen 2. In reality, Gen 2 had 3 afflicted males. We got it. We got the 3 afflicted males. Gen 2 had 4 carriers. We had 5. Again, this is a pretty accurate model, considering that it was just a probability matrix. Nature turned out pretty good so far. But we are going to reach a point where nature and probability diverge. And then other than that, Gen 2 had 4 healthy males. We had 5. And we have 3 healthy females. In reality, there were 5. Alright, now let's look at Gen 3. This is where they diverge. We have 4 afflicted males. On the other side of your screen, you will see that there were 6. And we had 7 carriers. On the other side of your screen, you will see there were none. Gen 3 is where victorious hemophilia kind of died out. And also worth mentioning is, if you're looking on the other side of your screen, Nicholas of Russia, his whole family was assassinated, so that kind of helped wipe it out. Anyway, we had 7 healthy males. In reality, there were 7. Alright, cool. And then there was the one question mark where the child died in infancy, so we're not sure if he's hemophiliac or not. We're just going to kind of disregard that. And we have 5 healthy females in our chart, and in reality there were 9. So that's the discrepancy. We had much more carriers, they had much more healthy females. But yeah, we did it. Gen 0, 1, 2, 3. We did a pretty good estimation. Gen 1 and 2 were almost spot on. Gen 3 it was just a little wavy, and this was our presentation on royal family hemophilia. Hope you enjoyed it. Okay, hope you've enjoyed the presentation so far, and I kept saying this is a probability matrix. This is an estimation. So let's talk about why. Alright, so recall those who reproduced in Gen 1, there was one healthy male, two healthy females, one afflicted male, and one carrier. And remember the probability matrix we got for x2 was 3 tenths, 2 tenths, 3 tenths, 2 tenths, double zero. Alright, so this is an estimation matrix, and it works for the first generation, but after that, because in the first generation there's only two people, it's very straightforward. But beyond that, our probability matrix makes no assumptions, and it treats it equally likely that any of the 6 possible genotype mating pairings could happen. That's not what happened. In reality, those who reproduced were always reproducing with someone who was healthy. There was no time in which 2 ill people mated. So we can go through these Punnett squares and we can compare just how far off our probability matrix was to what really happened. And remember, this was a projection, so we just wanted to see how accurate we could get, making no assumptions. Just pure theory probability. So we get healthy female, standard one, we did this in the beginning, 2 healthy females, 2 healthy males, each 1 out of 4 probability, or excuse me, 1 out of 2 probability. Each block has a 1/4. And we get the same thing here, and we can multiply it by 2 because remember 2 females mated. And now we have a carrier, healthy female, affected male, healthy male, 2 carriers, and 2 healthy males. So it's interesting to note, an afflicted male can never produce an afflicted male. Only carrier females or healthy males. Alright, so now there's 4, 8, 12, 16. Remember there's 2 of these, so 20 total squares. So let's just put our probabilities over 20. And of course we're going to end with a double zero because there's no afflicted females, and the 6th row was always 0 to make it square. And let's just count them up here. We got 1, 2, 3, 4, double count, 5, 6, 7 healthy females. 1, 2, 3, 4, 5, 6, 7, 8, 9 healthy males. Went out of order there, my bad. And now let's talk about the carriers. 1, 2, 3. 3 carriers. So that means there must be only one of these, one afflicted male. And there is this guy right here. Alright, so in reality, this first one should have been just under 0.5. We're at 0.3. Second one we had 0.2. In fact, it was actually closer to 1/3. We had, so 0.33. And now here, 3 out of 20, that's 0.15. We had double that, 0.3. And last we had 0.2, here we had 0.05. And so that's why it's an estimation matrix, but as we saw through the diagram, it turned out pretty accurate. We're back with more math. Alright, consider, for our next example, we're going to talk about inbreeding, which, just so we're clear, is when 2 people or animals or what have you, very closely genetically related, mate. Okay, now suppose nuclear war happens, and only a small rural county in Alabama is untouched by the nuclear fallout. A population of humans must survive by inbreeding. Pretty reasonable. And specifically, sibling inbreeding. Further consider a peanut allergy that is present in this community and is tied to the recessive gene lowercase p. Remember, it's recessive. So as long as they have at least one dominant gene, they're safe. But if they have both recessives, now they're allergic to peanuts, which in an apocalypse could cost you your life. There's not many food options. You gotta eat what you get.
So as you can see, our nth generation vector xn is going to have 6 components in them, And so A sub n is going to be the probability that the sibling pair mated in the nth generation is type capital P, and capital P, capital P. And so B sub n, C sub n, and
It follows suit.
through S sub n follow suit.
Okay, let's find M. We're going to find one column and the rest are the same process. So I think it does justice to just do it once. Alright, so consider mating someone who is a carrier of the peanut allergy with someone who is also a carrier of the peanut allergy. Now, there's a 1/4 chance of this, 1/4 chance of the affliction, and a 1/2 chance that they carry it. So, what is the probability that we pair two siblings like this? Well, it's the probability of this times the probability of this, 1/4 times 1/4. And we go down here. That would be 1/4 times 1/2. But remember, this is equivalent to the reverse pairing. So it's 1/4 times 1/2, double it because it happens twice. And it goes all the way down the line, and our final probability matrix looks as such.
Finding all of our probabilities, as shown, we get the probability matrix to equal this nice thing.
Here's the column I was working on. We did these two.
Yes. And remember, xn is equal to mx to the n minus 1. And we're going to diagonalize this matrix, so then xn is going to be equal to sq, which is our diagonalized matrix, to the n s inverse times the initial conditions, the vector of initial conditions.
And we've already shown how we got to here, so this is S. Find S inverse, and we're going to give you Q. Okay, we got Q, which is the diagonal of M. These entries on the diagonal are our eigenvalues. And now we can raise everything to the nth power, and recall we'll get S times Q to the n times S inverse, and that will tell us what this peanut allergy does over time.
Okay.
Say okay. So we got this, we raised Q to the nth power. Our initial conditions, I just said let's do an even distribution, that seems plausible. So 1/6 everywhere all down the line. Remember, it's a probability, so it has to add up to 1. And now we take the limit as n goes to infinity of this quantity here, and the moment we've all been waiting for. What is it going to give us? It gives us 1/2, 1/2, and the rest are just big fat zeros. So half the people will be dominant, and half the people are going to have this allergy.
Markov chains rule.
Welcome back. I'm your host, Matthew Bruno, and get ready for our next guest. Say okay. Our next guest is a man who does need an introduction. He is a mathematics student at Edinburgh University and the architect of the simulation that we all currently live in. Give a warm welcome for Jacob Heidlock.
Thank you very much. Thank you very much. No,
Yes.
quiet. Your pause is not necessary.
How you doing, Jacob?
I'm doing pretty well. How are you doing?
Thanks for coming. Thanks for coming.
You're welcome.
I was surprised we got you. You got a lot going on.
Yeah, I really do.
I mean, what do you do in your spare time? Do you have spare time?
Yeah, I do have a little bit of spare time. Generally, I like to dig through people's trash to find DNA samples. I like to start new cults for alternate revenue streams.
Nice.
And the thing I'm most passionate about is my public outreach program, where I explain how Markov chains can be applied to genetics to kids.
Wow. None of that was interesting but that Markov chain. What did you say about genetics?
Markov chains can be applied to genetics.
Whoa, what is a Markov chain?
Well, all you need for a Markov chain is a finite number of states and transition probabilities, which tell you the probability that the system is in the state I, given that the system was in the state J. These probabilities are denoted. Do you have a marker?
Yeah, none of this is making sense. Why don't you write this out for me? Yeah.
These transition probabilities are denoted P sub I J, and they tell you the probability that the system is in state J. The system is in state I, given that it was in state J. These probabilities can be constructed into a matrix to give you the transition matrix for the Markov chain.
This is all a lot.
Yeah.
This is a lot to take in. Should we go through an example?
I was not there yet. We're good. Consider the case of a self-fertilizing plant. In this case, our Markov chain has three states: capital A, capital A, capital A, lowercase a, and lowercase a, lowercase a. In self-fertilization, each offspring inherits both alleles from one parent, which is similar to autosomal inheritance, where both parents have the same genotype. Thus, our probability table looks like this, derived from the autosomal probability table where both parents have the same genes. Thus, the probability transition matrix looks like. And the system can be expressed as a Markov chain as follows.
This is really interesting, Jacob. Why don't you tell us some more?
Okay, I will, Bruno. As you can see, this Markov chain has two absorbing states: capital A, and lowercase a, lowercase a. Since once they are at these states, they return to these states with certainty, or probability 1. You can diagonalize M as before, finding the determinant of lambda I minus M. And this turns out to be lambda minus 1 times lambda minus 1/2 times lambda minus 1. And we set this equal to 0. This gives us the eigenvalues of lambda equals 1 with an algebraic multiplicity of 2, and lambda equals 1/2 with an algebraic multiplicity of 1. Now that we have our eigenvalues, we can find our eigenvectors by reducing matrix. For lambda equals 1, augmented with the 0 vector. This gives us a whole bunch of zeros. And so our eigenvectors for the eigenvalue lambda equals 1 are 1, 0, 0, and 0, 0, 1. You can find the eigenvectors for lambda equals 1/2 in the same way. When you row reduce this, you get 1, 0, 0, 0, 1, 0, negative 1, 2, 0, augmented with 0 vector. And this gives us the eigenvector 1, negative 2, 1. Using these eigenvectors and eigenvalues, we can construct our P and our diagonal matrix D. So D is going to equal 1, 0, 0, 0, 1, 0, and 0, 0, 1/2. P is going to equal 0, 0, 1, 0, 1, 0. And 1, -2, 1. Thus, x to the n, the nth generation, is going to be equal to 0, 0, 1, 1, 0, 0, 1, -2, 1, times 1, 0, 0, 0, 1, 0, 0, 0, 1/2 to the n, and times the inverse of p, which is 0, 1, 0, 1/2, 1/2, -1/2, and 1, 0, 0. And this will be multiplied by our x sub 0 vector, which is our initial conditions a sub 0, b sub 0, and c naught. Multiplying this out yields the solution vector a naught plus b naught times the quantity 1/2 minus 1/2 to the n plus 1, 1/2 to the n times b naught, and in this last entry we'll have b naught times 1/2 minus 1/2 to the n plus 1 plus c naught. Going back to a system of equations, we have a sub n is equal to a naught plus b naught times the quantity 1/2 minus 1/2 to the n plus 1. B sub n is equal to 1/2 to the n times b naught, and c sub n is going to be equal to b naught times 1/2 minus 1/2 to the n plus 1 plus c naught. Taking the limit of each of these equations as n approaches infinity gives us a sub n approaches a naught plus 1/2 b naught, b sub n approaches 0, and c sub n approaches 1/2 b naught plus c naught. So as you can see, the homozygous dominant genotype is an absorbing state, as well as the homozygous recessive genotype is an absorbing state.
Hey, good interview, Jake.
Thank you.
You know, I learned a lot.
I'm really glad.
Markov chains and genetics, very interlinked.
Yeah, and linear algebra. That's the greatest part.
Wow, what a great presentation.
Yeah.
I wonder how it could get any better.
I mean, we should get an A for this, right?
Oh, man.
Pompous math majors.
All right, let's take a recap, shall we, Jake?
We shall.
Well, we started off real hot. We were talking about chicken breasts, and a breeding program so that all of our chickens would have large breasts.
Yes, under autosomal inheritance.
That's right.
Where, remember, each individual inherits one gene from each of their parents.
And then we moved on to X-linked recessive.
Yes, we looked at hemophilia in the royal family and
We projected how it would affect the royal family, given that a carrier mated with a healthy male, and then we compared that to the actual historical data, and it came out pretty accurate. Then we talked about nuclear fallout and inbreeding.
Yes, and we looked at how a population can drift to the homozygous genotypes through inbreeding, and how that can give a large portion of your population a peanut allergy.
That's right. And then, just when you thought it couldn't get any more exciting, we started talking about Markov and his chains.
Yes, and Markov's chains rule.
Yes, no doubt about that. And tell us, Jake, how do the Markov chains, how do those relate to genetics? What do they tell us?
Well, we can model inheritance through Markov chains by letting the states be the different genotypes, and the transition probabilities are the come from the same tables that we used in the autosomal case. Or you could also model X-linked inheritance with that as well.
That's right, a lot of power in these chains.
Yeah.
Hey guys, thanks for watching. I hope you had a fun time. Jake and I worked really hard on this video, and I think it turned out really well. I hope you learned a lot. I think it was really educational, while also very entertaining. That was our goal from the start. We put a lot of work into this, and good luck on our problems. I look forward to watching your videos. Please enjoy the credits as they roll by. Jake, anything you want to end on?
Did you see all those dogs?
Jake, anything you want to end on?
Make sure to rate, comment, and subscribe.